Bismillahirrahmanirrahim. So today, inshallah, we're going to start chapter 3 to talk about public cryptography and message authentication. The book is taking a slightly different angle from any other book in cryptography, where usually public key cryptography is usually discussed with symmetric cryptography, because the only difference is that this uses 2 keys and the other one uses 1 key. So in a way they are related. But here the book takes another angle, where it actually discusses cryptography, or discusses the public key cryptography based on functionality. So public key cryptography, as we will see later, it's actually mainly used for message authentication. So that's why it's actually grouped in this chapter to be combined with message authentication. So we're going to talk about message authentication in the first half of this chapter, and then we are going to transition into talking about public key cryptography and talk about the different usages of it. So we know that for confidentiality, we talked about encryption. So encryption is used to protect against passive attack, eavesdropping. So that's basic. We talked about this. But as we said before, confidentiality or encryption in general does not protect against manipulation or against active attacks where the message can be manipulated on the channel. Okay, so there is a possibility that the attacker may actually modify the message. Okay, in which case the encryption algorithm cannot do anything about it, because it's designed for passive attacks. It's designed to conceal or hide the message. But if you manipulate the message, it cannot really do anything about it. So in a way, we need another component. Okay, in addition to encryption itself is not enough. So protection against such attacks is known as message authentication. So in order to protect the message against this kind of manipulation, we talk about another component, which is message authentication. And by message authentication, we talked about the entity authentication or peer entity authentication and message authentication. There is a slight difference between the two. Entity peer authentication talks about the fact that, if you have a connection with another party, like a server or something, then you authenticate yourself, which means that you identify yourself to the server, and this is for the entire communication, right? And that usually uses slightly different authentication techniques, like similar to the fact that when we log on to Blackboard, what do? We use two-factor authentication, right? We provide our credentials, and then we receive a code, and so that's A for peer entity authentication. For message authentication, that's also required. So every single message in the communication needs to fingerprint my identity in it. Okay, so that the server or the other party, it has confirmed that this is indeed Amr who is connecting, but every single message has to embed this information into it, so that every single message coming from that user, and make sure that it's coming from that user. Okay? So message authentication, which is the main topic of this chapter. We will talk about other types of authentication in later chapters. But message authentication here is the identity of the user, okay, which is fingerprinted and embedded in every single message throughout the communication. So as we will see later, this has 2 very important aspects. One, it identifies that user. It makes sure that this message is coming from that user and not anyone else. Okay? The other component, which is also as important, that the message itself has never been manipulated. So we need to achieve these 2 objectives as part of the message authentication. So these are the 2 components highlighted here. So the 2 important aspects are to verify that the content of the message has not been altered and the source is authentic. Okay? How do we do this, There are 2 ways of doing that. maybe we can use conventional encryption as well. As we said, conventional encryption algorithms, in fact, in a way, it implies where the message is coming from. Why? Because the message itself embeds in it the key, right? And the key is only known by the source. So in a way, we can, make sure that this message is coming from that source and not anyone else, because only the source knows the key. Okay, so let's build on that. Okay, so let's try to leverage encryption techniques, because we know how to do that. These techniques have been well established. So let's try to do that. Okay, but the bad news here is that symmetric encryption alone is not a suitable tool for data authentication. Why? On one hand, it does not prevent message alteration. If the message has been manipulated on the way, right, then I have no way of figuring out that the message has been manipulated, because encryption techniques are designed for passive attacks, right? And if the message has been altered, the decipher or the decryption algorithm will decrypt the message as if it was not altered. And in fact, you will experience that in assignment 2, where you will decrypt the message, and then you will find that the message is actually corrupted just by introducing simple manipulation to some of the blocks, right? So the fact that we assume that only the sender has the key, that's good, because then we can embed and fingerprint the message, every single message, with the key that is coming from and only known by the source. So that part we can guarantee, but we cannot guarantee that the message has not been manipulated. That cannot be done. ماشي? Also, if the message includes a timestamp, the receiver assumes that the message has been delayed beyond that normally expected. So even if a timestamp or anything in the message has been manipulated, right, the receiver will not know that this has been manipulated, right? Even if it's encrypted, we don't have any way to figure out that any part of the message has never been manipulated before.
But Doctor, isn't it hard to manipulate an encrypted message? Like you just can't.
It's very simple. In fact, you will do this in assignment 2.
Yeah, but not in a meaningful way. Like I can't just to be corrupted the message when decrypted, but it cannot be manipulated in a meaningful way. So, for example, I cannot change the name of a person inside the message if it was encrypted, right?
Right. So any part of the message that has been altered or manipulated, okay, the encryption will not know. The decryption will happen without knowing that this message has been manipulated in any way. Okay, whether even if I know some component, يعني مثلا if I'm sending a packet, some parts of this packet might actually be exposed, like for example the protocol level format or the header. Okay, sometimes the header is not to be encrypted for reasons that we will talk about later, right? So even if any parts of this مثلا protocol level format has been altered or updated, I wouldn't be able to tell. I wouldn't be able to know. Okay. So in other words, what we are trying to see here, what we're trying to say here, is that encryption could be useful, but it's not sufficient. Okay, we need something in addition to that. Okay, that's the whole message. So without message encryption, an authentication tag can be generated. This authentication tag will be actually, as we will see, this is the message. Whether the message is encrypted or not encrypted, we don't care. Okay, because that's not our objective. What we could do using this method is to actually append something to the message. Okay, we'll call it for now tag. Later on, we'll call it a MAC, or message authentication code. And this tag will achieve the two objectives we talked about. It embeds into it, okay, the source identity in a form of a key or something. ماشي? So it embeds inside it the identity of the source, and it's produced in such a way that if there is any part of the message altered here, this tag will tell us that this has been altered. Okay? So the message itself may not be encrypted or encrypted, doesn't matter. That's not our focus. ماشي? So the message is not encrypted, message confidentiality is not provided. So in that case, whether the message is encrypted or not, not encrypted, it doesn't really matter. Okay? As we will see in a minute, يعني. So that's what we call message authentication code. Okay, so what we will do as part of this chapter is that we have a message, okay, and then we will produce through like some message authentication code algorithm, we will produce a MAC, okay, which is a tag that gets added to the message. Okay, not by encrypt the message itself, no, we add it to the message. Okay, and then we'll transmit the message similar to what we used to do before. Okay, if the message has been altered, then this tag will tell us. One thing we notice here is that the requirement for MAC is not to be reversible. We don't need to reverse the MAC. Or from the MAC we reach to the message. This is different from encryption. Encryption requires decryption.
This is hashing.
Yeah, so this is not only hashing, this is something else. What I'm trying to emphasize here is that our job is not to reverse the MAC in any way. What we will do at the receiver side is that we have the same MAC algorithm. We will take the message, okay, assuming that the message has been altered, we will try to reproduce MAC again. And if the MAC that we produce matches the MAC that comes with the message, then and only then we say, yes, okay. Okay? But our requirement is not to reverse that in any way, or to generate part of the message from the MAC. That's not our purpose. Okay? So we will try to calculate the MAC again at the receiver, as if we don't know anything about this MAC, just from the message content. And if the two MACs match, then خلاص, we say the message is authenticated, and then we accept it. Okay, كده? That's the type. One class of techniques which is used to produce that MAC is the hash functions. Okay, hash functions have been there for a while. The problem with hash functions is that it does not have any way to embed the identity of the source in it. In other words, it does not use a key. Okay, so hash functions does not use a key. Hash functions, what it does is that, again, it takes a message and it produces a hash, okay, which is, again, another function on the message itself. Okay, it doesn't take a key. Unlike encryption, it doesn't take a key. Okay. So if this hash, assuming that this hash is strong, it will achieve one objective, which is to protect the integrity, right?
Yes.
So if the message has been manipulated in any way, okay, assuming that I can reproduce this hash on the receiver side, okay, I will be able to match the two hashes and then say that the message has not been altered. But I cannot authenticate the message because the hash function does not take a key. Okay?
Doctor, I have a question.
تفضل.
So this hash is appended to the message, right?
Right.
So can an attacker, assuming that, like we said, the algorithms are known and the hash doesn't take a key, can the attacker manipulate the message and the hash that is appended?
That's the main topic of today. That's what we will talk about. That's what we've been talking about now. Okay, yes. Yeah, the quick answer for your question is yes. Of
That's
course.
the issue.
Yes.
It doesn't take it.
And that's why we say that this hash is strong and this hash is not strong. Okay? But can it? Yes, it can, of course.
And, for for the authentication part, since the message is encrypted, then the two objectives have been achieved.
Yeah, so what we're trying to say here is that hash functions are good, but again, not enough. So دلوقتي we have encryption is good but not enough, and hash functions are good but not enough. So we are trying to motivate the fact that we need both. Okay, so we need to integrate both. Okay, so that's how we do this. Okay, so we can do this using three different ways. Okay, and this is important. Yeah, I need your focus here. So one way is to produce the hash, which has a signature of the message. We call it a message digest. ماشي? So this will produce message digest. Okay, and then we embed this the source identity through like some encryption, and the encryption can be done using encryption, symmetric key encryption. Okay, so this now we call it a MAC. Only now we call it a MAC. Okay, because it has the signature of the message, it protects the message from alteration, and then it embeds the identity of the source. Okay, so it achieves both. So now we call it a MAC. Okay. Then we append the MAC to the message, and then we send the message over the channel. And then on the other side, again, we don't reverse anything. What we do is that here, we again produce the hash at the receiver side without looking at the MAC خالص. We produce the hash, okay? And again, we try to encrypt the hash using the key that we have, right? And then and only then we compare the two hashes or the two MACs. If it matches, then خلاص. Okay? واضح كده البروسيس؟ طيب, this is using symmetric encryption. We could do the same using public cryptography بقى. Okay? In public cryptography, what happens is that the only difference is that like when we have a source, okay, and it's trying to send a message to the destination, assuming that we are trying to achieve confidentiality. Okay, so the only difference for public cryptography is that we have two keys. We have private key and we have public key, right? Okay, so what do we use for encryption? For the case of public key, for the case of public cryptography, what do we use for, which key do we use for encryption? The public key. Okay, so here we need to use the public key. Okay, and then we produce the encrypted message and then we send it. Here we decrypt the message using the private key. Okay, that's what so if I want to send a message to Ahmed should have actually exposed his public key to everyone, including myself. Okay, so if I need to encrypt any message or communicate with Ahmed, then I need to use his public key. And we'll talk about the motivation why we need two keys and so on. Talk about that. Why did I talk about confidentiality here, even though we are talking about message authentication? Because for public cryptography here, remember, we never use public key to embed the identity of the source. The public key does not identify the source. It's known to everyone, right? So what's not known to everyone? The private key. So if we need to produce the MAC, we don't use public key. We use the private key. But for public cryptography, remember, it's like a mirror. So if you encrypt something using the public key, you can decrypt it using private key. If you encrypt something using a private key, you can decrypt it using public key. Okay? So that's the main difference here, is that for confidentiality, we always use the public key to communicate with the destination. if we're trying to authenticate the message, we use our identity, which is the private key, not the public key. So when we produce the hash, after that we use the private key, and then we produce the MAC. ماشي كده؟ تمام. Then it's the same. And then the verification of the MAC on the other side uses the public key. Everyone has it. Everyone can verify that it's me. Okay? Because everyone has the public key. Okay?
So in this, so we will be using two pair of public-private key. One for the message integrity. And
of course. Yes, of course. You have your own private key, and everybody has your public key, right?
Because
similarly, you have the public key of others that you want to communicate with. Okay? طيب. The problem with encryption is that it's expensive. Okay? So the question is, can we achieve the same objective without having to do encryption? Why? Because encryption is complex. We know that we have to do it for confidentiality, because we need to have it reversible, right? It has to be reversible, so we need to have it reversible, right? So reversibility is a condition for confidentiality. It's not a condition here. So the question is, can we avoid using the complexity of encryption yet achieve the same thing? And the answer is yes. So instead of encrypting a hash, what we will do, we will embed the identity together with the message, append it, just append it, okay? A secret, we call it a secret, okay? This secret only is known by the source and the destination. Could be the key. But هنا I will not do encryption بقى. The main hack here is that I will append the secret to the message and hash everything. That's it. Right? Because I don't have to reverse it. You know, the important thing here, I don't have to reverse it.
So even if the attacker detects or identify the secret key, there is risk.
لا.
There is risk.
ما هو احنا اصلا بص, the whole cybersecurity is built on a simple assumption. The key is not known to the attacker. If the key is known by the attacker, all what we're doing is useless. That has to be clear. Okay? If the key is known to the attacker, then what we are doing is useless. Okay?
Because using the third method,
أيوة.
like eliminate the advantage of using public.
Yes, exactly. So this is the important thing we achieved here, is that we don't do encryption. Why? Because we don't have to reverse anything. Okay? So هنا, what will happen is that we will, why we call it secret key? Because now it will be communicated over the channel bar. Okay? And here I can read the message, append to it the secret key, as part of the, append to it the secret key, and then I will do the same hashing again.
So the enemy wants to talk to regarding the power, they're outside.
Okay? All right, so that's how, the main thing we achieved here is that we didn't have to do encryption, because we know encryption is expensive. ماشي كده؟ طيب, so hashing itself, as we said, it's good, but it's not enough. And in all the three methods we used in the previous slide, hashing is an integral part of this procedure that we're trying to do. So it's important not only in the message authentication, but in digital signatures in general. And as we will see later, there is like some protocols that use digital signature even without having to do authentication. So hashing functions are used in many areas. Type. The purpose is to produce a fingerprint. Again, the idea is not to from the fingerprint to reproduce the message. There is no reversibility condition here. بالعكس, as we will see, reversibility should be really hard, or actually not hard, impossible. Okay? طيب. And to be useful for message authentication, the hash function needs to have these properties. In order to be used for message authentication, we need to highlight these properties. These properties are very, very important, especially the last two. Okay? So hash can be applied to a block of data of any size. Okay? So that the message digest itself has a fixed size, regardless of the original message size. But the message size can take any size. Okay? But any size, يعني, to a limit. يعني. Okay? As we will see, the message has to be below certain limits, but it can have variable size. واضح كده? So that's first. H produces a fixed length output, so the message digest itself is fixed length, regardless of the fact that the message itself is variable size. So H of X, or the hash of the message, is relatively easy to compute. Again, that's otherwise we can use that as some kind of encryption ولا حاجة. يعني we want to make the produce of the hash value to be as simple as possible. Okay, especially that we want it to be implementable using hardware and software, because we can actually use, in a way, we can use مثلا DES ولا triple DES, but it's very expensive. So the idea is to try to avoid completely having to use any of the encryption algorithms, particularly the ones that use a bit level manipulation like DES and triple DES. So we wanted to avoid this. So the hash function needs to be simple and easy to be implemented using hardware and software. Okay? طيب. The last three are very important. So for any given code H, okay, it is computationally infeasible to find X, an input message, okay, such that the hash value is H. And what that means is, if I give you a certain hash, okay, of fixed size, this is a hash, okay. If I give it to you like this, can you in fact produce a message so that when you apply the hash function, you can produce H? This is actually this is the reversibility. So if I give you a hash and you can produce the message, then this makes the hashing reversible, and that's actually that's not supposed to happen, because otherwise, يعني إيه بقى, if anyone knows the hash, then they can reproduce the message itself. Okay, so that's not supposed to happen. Okay, so if you know only the hash, it is computationally infeasible to produce a message that has this hash. In other words, the hashing should never be reversible. Should not be reversible.
How can the receiver decrypt the message if he didn't know the hash?
Eh?
How the receiver decrypt the message if
Because the receiver has the message. The receiver has the message, right? So they will try to produce the hash from the message. And only if the two hashes match, then it says, oh, okay, I will accept it. But if the receiver knows only the hash, okay, it cannot reproduce the message. Okay? That's not supposed to happen. ماشي كده؟ And طبعا the reversibility is هنا برضو التعبير بتاع خد بالك computationally infeasible. ها؟ I said impossible. I shouldn't say impossible. لأن هي it's always possible, صح؟ Using brute force. صح؟ I can take a hash function and take all the combinations of the message itself, okay, and apply the hash function until the hash itself is h. صح? I can always do that. But it's computationally infeasible. Okay? So for that, there is a theorem. We'll talk about it. It's called birthday paradox. Okay? The birthday paradox says that you can always use an algorithm to produce a message to have this hash with a complexity of O of 2 to the power n over 2. That's if you know the message length. Remember using brute force, احنا قلنا brute force in order to attack and know the key, right? By knowing the cipher, you can, in fact, if you know the length of the key, then you can attack using a complexity of O to the power A 2 to the power n minus 1, صح? لا هنا it's way below. Okay? It's easier, but still we need to try to make this computationally infeasible. Okay? ماشي كده؟ طيب. So that property is very important. طيب. Another one, for any given block X. So now I will not give you H back. Hold back. I will not give you H. I give you a message. Okay? This talks about the integrity part. If I give you a message X, okay? If I give you a message X, you can reproduce the hash very easily. صح? طيب. But that's not what we're talking about here. What we're talking about is that can you produce another message Y such that h of X equals h of Y? What this tries to say is that if I give you a message, can you manipulate the message in a certain way such that it produces the same hash? This is what you were talking about, right? صح كده? And again, here we use the term computationally infeasible. Okay? It should be computationally infeasible. We didn't say impossible. Why is it always not impossible to have two messages to have the same hash? You can never design a hash function such that you don't have two messages that have the same hash.
Because the length of the hash is smaller than the messages.
ماشي. So
if you want to summarize
limited combinations.
yeah,
Yeah.
exactly.
Limited combinations.
okay, let me rephrase what you just said. So assume that the message itself has a length of m. Okay? How many combinations you have for the input message? 2 to the power m. Assuming that this message is binary, يعني. At the end of the day, this message is binary, صح? So the message has a combinations of 2 to the power m, صح? Okay. If I have a hash of length k, okay, remember that the hash value has a length which is much less compared to m. طبعا, صح? We said that the message can take any size, but the hash itself is small. So the number of combinations for the hashes is actually 2 to the power k, which is also very low compared to 2 to the power m, right? So you always have two messages that have the same hash. Okay? You always have that. But the idea is just to make this hard. Okay? If you have two messages that has the same hash, we call this collision. ماشي? It's like collision. ماشي? So you always have collision. But a strong hash function makes this collision hard. As hard as possible. Especially that if I give you X. If I give you a message X, assuming this message X, okay, can you in fact produce a message Y such that the hash value is the same? Theoretically, yes, but this should be as hard as possible. If I give you a message X, then what you will think about is that, okay, so let me try to rearrange the message in a certain way, okay, such that the hash value is the same. Can you do that? We'll talk about a very, very simple example for this that will make this clear. ماشي? So the difference between this the difference between this okay. The difference between this condition or this property and this property is that here I don't give you X. Can you in fact have any two messages, X and Y? I don't give you X بقى. ماشي? You don't have an input message. If you have an input message, what you will think about is to rearrange the message in such a way to produce Y. Okay? I didn't give you the message. Can you have any two messages? In which case you have more degrees of freedom. صح? Can you actually produce two messages that have the same hash? برضو this should be computationally infeasible. So these properties are very, very important for the hash.
How is this useful to the attacker?
Which one?
The last one, to have two pairs of messages that have the same hash.
The last one?
Yes. How is it useful to the attacker?
That's a good question. That's a good question. I don't know. يعني if you have X, then the attacker captures a message X. He or she can modify the message X. So he corrupted the communication, right? But if you don't have X, معناها you can produce two messages, but these two messages are not part of the communication أصلا. Okay? What did the attacker gain? Nothing. Okay? But this is to test the strength of the hash function. Okay? This is mainly to test the strength of the hash function. It's not for the attacker to get anything out of it. واضح? طيب. There are two approaches to attacking a secure hash, of course. One is the cryptanalysis. We'll see a very simple example for this. You have an example of a hash function simply based on parity bits. Parity bits we discussed, or you studied parity bits before. We'll see how it's produced. Very simple, okay? But as simple as it is, it's not considered to be a strong hash function because of the fact that يعني any primitive attacker will be able to manipulate X and get Y. The value of the hash will be the same. Very, very simple. يعني. So that's what we call cryptanalysis. ماشي? Otherwise, we can always produce some collision using brute force. Or we can, in fact, manipulate a message X to produce a message Y, okay, with some complexity using brute force techniques. Okay, brute force by exhaustive search. So that's a function, that's a very simple function, which is parity, using parity bits. So a message, a very long message, so very big long messages, CRC اللي احنا we studied in network 1 يعني. Okay, you have a big message. You can always divide this message into blocks of, let's say, like 32 bits or 16 bits blocks. And then stack these blocks, one on top of the other. And then you do XOR for every single column to produce a hash of a length of 16 bits or whatever. Very simple. XOR all the blocks. Okay? That's يعني theoretically that's a type of hash برضو, right? Because you actually took a message of variable size. Of course, if the message itself is not if the message size is not divisible by 16, what do we do? Padding. We use padding. We can do padding. We can always do that. So a message variable size, we produce a hash of a fixed size. We can do that simply. But is this strong enough? Of course not, because if the value here is, you have مثلا value here based on XOR, so the number of ones here is odd, so we put 1. The number of ones here is even, so we put 0. Okay? So can you think of how many combinations do I have where the number of ones is odd? I can manipulate the message in many, many ways. And the hash will be the same. صح كده? So it is a hash, but it's not a strong hash. صح? So it's not to be considered a strong hash. So from X, I can actually produce Y's, يعني infinite number of Y's, okay? And the hash is going to be the same. So it does not fulfill one very critical property of hash functions. طيب الجد بقى, so Nest has actually produced a hashing technique called SHA, ماشي? Which was developed by Nest and published as the Federal Information Processing Standard, or FIPS 180. طبعا we don't have to memorize الأرقام ديت يعني. So the SHA was actually designed on top, or was designed based on an existing technique which was very widely spread, which is called MD4 or MD5. MD4 stands for message digest, okay? And SHA is, of course, is a secure hash, okay? طيب, the SHA or MD4 was based on a hash of 160. Okay? So 160 based on the birthday paradox. So we can, in fact, break this hash function or produce some collision with a complexity of O of 2 to the power 80, right? Nowadays, this is highly possible. Highly possible. Okay? So the first thing we thought about is that we need to increase this size. Okay? So we'll see how many data bits we use for SHA1 and SHA2. So SHA1, which is based on MD4, it uses 160 as the size for the data. All of these are part of SHA2. So SHA version 2 allows for 4 different hash sizes that starts from 2 to 4. Okay? So if the message digest is 160, then usually the message size, احنا قلنا variable size. But here we have a limit. We have a limit for the data size. Okay? Why? Because again, if you increase the message size a lot, then this increases the probability of collision. صح? The probability of the collision to happen. So although we say it's a variable size, but there has to be some correlation between this and this. If the message size is a lot larger than the hash size, then you are actually making the collision easier to happen because you have more degrees of freedom. Okay? Type. So this is the message size. What is the block size بقى? We didn't talk about block here. It's not a block cipher. So what happens is, similar to what we did for CRC, the way that we produce the hash is always by dividing the big message into blocks. Okay?
We have multiple hashes.
لا, هو at the end it's one hash. We'll see that. It's one hash, but this hash is dependent on all the operations that we do on all the blocks. We'll see how we do this. ماشي كده? So the block size is 512. And again, what if the message size is not divisible by 512? What do we do? Adding. ماشي? So that's easy to do. Okay? So here in SHA 2 to 4, so أصلا طبعا block size, and there is also a word size, and the number of steps. Number of steps is like the rounds. فاكرين number of rounds? Okay, this is number of steps. طيب. So the block size for 2 to 4 is still 512, and here it's 1024. Okay. The message size has not been changed until here as well. So again, there is some kind of correlation, but it's not one-to-one. Okay. طيب. So this is the birthday paradox. For n bits of hash, we can always create some collision with a complexity of 2 to the power n divided by 2. ماشي؟ طيب. So that's how to produce the hash. And we'll see there is some similarity with the concept that we do for encryption. بس لا احنا اتكلمنا عن ايه بقى؟ We talked about one mode of operation. Remember, one mode of operation is called cipher block chaining?
Yes.
So this is in a way like block chaining, but the difference here is that we divide the message into blocks, right? The good thing about cipher block chaining is that everything in the future is based on the history, right? So the ultimate hash is dependent on all the blocks before it, okay? And that's why, but unlike the mode of operation, what we did is that we produce the cipher text block to block, and then we take all these blocks to be the cipher. No, here we don't do this. We only take the last hash. Okay? So this last hash is actually a function of all the ones before it. ماشي? But in a way, you see that there is some similarity to the cipher block chaining, which again you will experience in assignment 2. You will be able to do some hands-on work on these modes of operation. ماشي كده؟ So this is SHA 512, which uses a block size of 1024 bits. ماشي? This is the blocks, okay? And this, if there is a difference, then we use a padding. Padding is very simple. These bits are predefined. 1 and then 0 with whatever size you want. But remember, because you are doing padding, you always have to store the unpadded length of the message. صح? So that's why we have L here. So the maximum length of the bits is 2 to the power 128 for the SHA 512, and that's why we have the last 128 bits to represent the length of the unpadded message. Okay? So the padding bits will be in between. Okay? طب السؤال بقى يعني صفصطائي شوية. What if the message is divisible by 112? We have to add one full block of padded bits and 128. Okay? We always have to store the length of the unpadded message. Anyway, so other than this, so we take every block. What we do is that to pass this through a function similar to again in encryption. بس هنا طبعا الفانكشن is we don't use بقى substitution و transposition. لا هي it's actually some simple permutations and XORs. That's it. Simple permutation and XORs. That's it. ماشي? And remember, this has to be very simple to implement in software and hardware. ماشي كده? So this length is actually 124, right? And here the key is 512. So the function takes from one side the whole block, 1024, and it takes the hash. The hash itself as a length is 512. So what is H0? H0 is actually initial vector. Okay? And this initial vector, by the way, is fixed. It has a fixed value. In the standard, they put it as a fixed value. ماشي? And then starting from here بقى you chain the output here, is 512, and then you chain it to the next one and next one and next one. Okay? So the structure itself has some similarity, except that the function here, again, the function here can be anything. The standard does not dictate a certain function, although it puts some requirements on this function that it has to be simple. Okay? So we can say that the hash at step I, okay, equals to what? Equal hash at step I اللي هي دي, okay, is the function of mi and hi minus 1, okay? And then you modulo addition, this is modulo addition, okay? We'll talk about modulo arithmetic in a bit, okay? Modulo arithmetic with a hi minus 1, okay? That's it. Again, producing this simple equation from this complicated structure makes it again easy to analyze, similar to what we did for the fizzle structure. So just by representing this whole thing using one simple equation, we can take this, we can apply by information theory, we can calculate certain probabilities and so on, conditional probabilities, the joint distribution, and then we reach to certain conclusion that this structure is strong. ماشي? Luckily, we don't have to do that. طيب. So this is the hashing. It's not a MAC. صح? It's not a message authentication code. ماشي? So Nest produces the SHA, which is good, but it's not enough for message authentication. For message authentication, we need another component, which is the authentication part to embed the identity. So there has been an increased interest in developing a MAC derived from the SHA. So one way is to use by encryption, as we said, but this is not what HMAC as a protocol or as a technique tries to do. HMAC uses the third method, which tries to avoid encryption. Okay? So we'll embed the secret value, and then we'll try to hash everything. Okay? So it looks like the HMAC is simple. It's just to embed the secret value in a way and then hash everything. صح? So in a way, it's simple. So there have been a number of proposals for incorporation of a secret key into an existing hash algorithm using the third method that we talked about. Okay? So this has been done by IETF, not Nest. Again, you don't have to really know who did who, مش مشكلة يعني. But this has been done by IETF. That's why it's done as part of RFC. RFC is produced by IETF. الناس بتوع Network 1 يفتكروا يعني. ماشي? But FIPS is Nest. ماشي? Not that it makes a big difference for us. And طبعا ال HMAC is being used in all the protocols that we will talk about later in the next part. It's used in TLS, it's used in wireless, in IPsec. Why? Again, because it's simple. It tries to avoid using encryption. It still uses keys, but in a way that's much simpler compared to using encryption. For confidentiality, we just have to. Why? Because of reversibility. Right? But here we don't have to reverse anything. ماشي? So the HMAC design objectives is to use without modifications available hash functions. SHA is available. So in particular, hash functions that perform well in software as well as hardware. So that's good. So SHA has proven to be very efficient. It can be implemented using, it's widely spread actually, and the code is public and it's widely available. It's standard. It's easy to analyze, okay? Computationally infeasible to produce collisions. So it's actually proved from many ways. So to allow for easy replaceability of the embedded hash function in case faster or more secure, which is again tries to avoid using encryption, to preserve the original performance of the hash function without incurring any significant degradation. So just embed the secret and hash everything. So the overhead here is not significant. ماشي? To use and handle keys in a simple way. Again, the secret is supposed to be a key at the end. Okay, but here the key is not to be used for encryption. To have a well-understood cryptographic analysis, which is what we have done. We have produced one simple equation that describes everything. صح? So this equation makes it easy to analyze. So you can think of the fact that HMAC, what it does is that it actually adds the secret key and does the hashing. Okay, not that simple, unfortunately. So what it does is that it uses that on two steps. Okay? So the key, this is the secret. Okay? So instead of appending the secret in one step and hash everything, no, it does that based on two steps. So it uses IPAD, and IPAD and OPAD are nothing but a masking registers that mask the secret. Okay, so it takes half of it. And then it appends that half to the message, and the message are blocks. Okay, and then it applies hash to produce the first part of the hash. ماشي? So this hash is based on the message plus half of the key. Okay? And then use that key as a message and add to it the other part of the key. Okay? So, and then use the hash again. Okay? To produce by the HMAC. Okay? Why two steps? I really don't know. It has there is a meaning to it. But remember, the first step is done to the entire message. The second step is only based on the produced hash, which is very small. So this second hash is much, much simpler compared to this, right? Because it applies to the hash plus the secret value, or half of the secret value. So this hash will be much, much faster in that case. But they do it on two steps anyway. ماشي? I guess to increase the difficulty of producing the collision. What HMAC tries to do is to avoid this. This is called CMAC بقى. The CMAC actually came before HMAC. CMAC uses encryption. Uses encryption. So they said, okay, so we can in fact use cipher blockchaining, similar to cipher blockchaining, but we will, because cipher blockchaining, it tries to chain every block to the next. So in a way, we can use that concept to try to produce an ultimate MAC, which is based on everything else. Okay? So what we could do is to simply divide the message into blocks, okay, with the size of the hash that we want. Okay? And then encrypt, and then use that encryption to be XORed with the next and next and next. But here the difference is we don't actually use all the encrypted parts. What we do is to use the ultimate one. Okay? And the ultimate one is XORed here with a sub-key value. Again, this key, from this key, we produce K1 and K2. Using sub-key generation algorithm, similar to what we did for fuzzy structure. Very simple, yani. They're very simple to do. We can produce number of keys based on that key, right? So we use one key to be XORed at the very last step to produce the message hash. ماشي? Or the MAC, sorry. This is called the CMAC. C here stands for cipher MAC, cipher-based MAC. Okay? And there are two simple cases. You don't have to really know the details about the difference between them, but this, the one above, in case the fact that the message length is integral multiple of block size. يعني if the message size is divisible by the block size. معنى صح يعني we don't have to add
Padding, right?
the padding. However, here we add one full block of padding. Padding because we always have to store the unpadded length. Again, these are details, yeah, you don't have to really know much about it. Okay? And this one, we don't have to add one full block. Okay, we just have to add the pad to part of the message and store the length as well. ماشي يعني difference is very fine. Yeah.
Using the previous block in the next
Chaining, yeah.
operation,
Yes.
the chaining is not recommended, right? Because of the error propagation. So we should avoid that.
لا خد بالك لا we don't لا مفيش error propagation هنا. This MAC is to be appended to the message. So if there is an error in the message itself, okay, this will allow us to only detect that the message has been altered. Okay? But that's not the requirement here.
But even if error
In fact, error propagation, لا, even if error happens to the message, to the MAC itself, لا خلاص ما هو ده في كل الحالات أصلا. If an error happens to the MAC, خلاص يعني you cannot do anything. You reject the message anyway. In all cases, you will reject the message anyway. طيب خلاص we can have a break هنا عشان طيب public key encryption, as we said, it uses two keys. This is the main difference. The first publicly available public key encryption technique was not even being used for encryption and decryption. It's called Diffie-Hellman, and Diffie-Hellman is not for message encryption and decryption. It's not for confidentiality. It's actually for key distribution. We will talk about this. It's for key distribution, and that's why is the chapter itself talks about public cryptography being used in something other than encryption and decryption. Okay, it's not for general purpose encryption and decryption. Type. So Diffie-Hellman is not to be used for encryption and decryption, but that doesn't mean that public encryption is never being used in encryption and decryption. There are general purpose public cryptography techniques or public ciphers that are being used for encryption and decryption in addition to message authentication, in addition to key distribution, in addition to other things. General purpose. One is called the RSA. This is the most important. طبعا most important معروف ليه طبعا. It's obvious from the names يعني. And يعني very proudly يعني الجمل is one of the اللي هو مراد الجمل. مراد الجمل is an Egyptian scientist who came up with one of the most يعني widely used public key cryptography technique. Okay, so we'll study RSA we'll study Diffie-Hellman, of course, and RSA in some details. Okay, and of course there is elliptic curve, which is another category of public cryptography which we'll not cover in this course. Elliptic curve is another category which we will not cover. Okay, type. Is asymmetric, of course, because we use two keys, public key and private key. Some misconceptions that are widely يعني available, but they are not true. إن مثلا public key encryption is more secure compared to symmetric encryption. That's not true. In fact, if you for the same size of key, symmetric encryption is even stronger or more secure. Okay. And that's why public key is actually is used in many ways nowadays, not for general purpose encryption and decryption. It's used for key distribution. We'll talk about this. Even RSA is used for key distribution. Public key encryption is a general purpose technique that has made conventional encryption obsolete. That's not true also. Yeah, some people say that, oh, public key encryption, this is the state of the art. All the symmetric encryption, AES and DES and triple DES is died. No, that's not true. And we'll see that. All the security services and protocols that we will talk about in the next part, they all use symmetric encryption. Some of them, they still use DES and triple DES until today. Okay? there is a feeling that key distribution is trivial. يعني هما what they say is that why public encryption is more important than symmetric encryption, because the key distribution is very trivial for the case of public key cryptography. Why? Because the public key, I can expose it, I can send it to everybody. No, it's not trivial. It's not trivial. You still have to have a protocol where you have to send your public key as part of a certificate, and there is like certificate management system. يعني it's not trivial, huh?
Third party.
Yeah, and you have to use the security certificate authority. We'll talk about this at the end of this chapter, or maybe next chapter, I can't remember. So لا, key distribution is not trivial for the case of public cryptography. We'll cover this, okay? So these are misconceptions. طيب, so this is the security model. Of course, we talked about security model before in chapter 1. So the security model for public encryption is that, well, if you have a plain text here, you have the encryption algorithm, whether it's using RSA or الجمل or elliptic curve or whatever. The way we do this is that every single source, or in that case Bob has his own private key and has a chain of public keys for everyone he wants to communicate with. Okay? And for encryption, not for Mac, for encryption, what we do is that if I want to send to Alice, then I have to grab from the chain, I have to grab the public key of Alice and then use that in the RSA algorithm, okay, to encrypt the message. When I do this, the only one who can decrypt it is Alice, because Alice has the private key, right? Okay. So that's the security model for. So if I want to encrypt with the private key, I use that for what purpose? For message authentication, not for decryption.
Digital signature.
For digital signature is to protect against the manipulation of the data. Sometimes, على فكرة برضو, this is confusing enough. Sometimes the message signature refers to message authentication, even though for accuracy يعني message signature refers to the hashing, okay, not to the authentication part of it, okay. But as we will see, like message signature standard, MSS, okay, it's a standard that actually uses message signatures to refer to message authentication. We'll talk about this. So anyway, so we can use the private key for encryption. So in that case, what we want is to embed the Bob's identity in the message, which can be verified by anyone, okay, to authenticate Bob. Okay, so these are the two security models that we use. Type. Public key systems are characterized by the use of cryptographic type of algorithms with two keys, as we said. One held privately and the other one is available publicly. Depending on the application, the sender uses either the sender's private key or the receiver's public key, depending on the purpose, whether we're using the public key cryptography for encryption and decryption, or we use it for message authentication. The use of public key crypto systems can be classified into three things. One is for encryption and decryption, as we said. For encryption and decryption, in that case, the sender uses that public key, okay, before sending a message to the receiver. We also use it for digital signature, and here we refer to the authentication, actually. Here we refer to the authentication, right? So the sender signs the message with its own private key, okay, to authenticate himself to the public. ماشي? Or for key exchange. For key exchange. Key exchange معناه ايه؟ I use the public key to exchange the symmetric key. Okay? So if I want to exchange a key with Alice, I can encrypt the symmetric key using the public key and send it to Alice. After doing this for one step, now Bob and Alice will have the same key on both sides. They can use symmetric key from now on. And that's in fact one of the very common ways of key distribution, is to use public key. Why we don't use public key for general encryption and decryption? Because it's more expensive compared to symmetric keys. ماشي? So it's one of the very, very famous ways for key distribution, is to use key cryptography. So these are the algorithms. So RSA is general purpose. You see that it's used for encryption, decryption, digital signature, as well as key. هنا digital signature, again, we refer to the authentication part. ماشي? Diffie-Hellman will see that's only for key distribution. That's only for key exchange. It's not, and we'll talk about why. We'll study Diffie-Hellman. We'll talk about why it's not being used for encryption and decryption. ماشي? Digital signature standard is obviously used for authentication. We'll talk about برضو DSS as a standard. The only one that we will not cover in this course is the elliptic curve. But again, elliptic curve can be similar to RSA. Is one of the techniques that can be used for general purpose public cryptography. ماشي؟ نيجي بقى للايه؟ للماث بارت. طيب فده again, this is not part of the book, but just to be able to decipher the puzzles in the book and really understand the idea behind RSA as an algorithm, ماشي? We need to take this crash review for modular arithmetic. ماشي? So first, what is mod function means? We all know that, صح? So if I say مثلا 8 mod 7, 8 mod 7 is a? Is 1. Why? Because 1 is the remainder of the division, right? صح? So the divisor is 1 and the mod is 1. صح? This means that if I say generally y mod x is n, this means that y can be represented as a multiplication of x such that the remainder is n. مفهومة دي؟ صح كده؟ So this way I can represent y as multiples of x such that the remainder is n. So that's fine. طيب. Now بقى we need to discuss the properties of this. Is the mod summative and multiplicative? And the answer is yes. So when we say that x plus y mod n, okay, this is exactly similar to x mod n plus y mod n. Okay? So that property is important. ماشي؟ واضح كده؟ So it's summative. ماشي؟ That means it's summative. طيب, it's multiplicative, which means that also x multiplied by y mod n equals to x. Actually, here there is another missing part. Why? Why do I did this? Why did I do this? Because when I calculate x mod n and y mod n and I sum them, the answer might be greater than n. صح? صح? The answer might be greater than n. So it cannot be greater than n. So I have to say that the summation mod n again. واضحة دي? Also here, x times y mod n is actually x mod n times y mod n and all mod n. So in a way it's a summative and multiplicative. واضح؟ دارسين الكلام ده صح؟ Okay. طيب, this is good. طيب, let's see. This is a warm up. Let's take the next step. ماشي. طيب, what is factorizing a number? Factorizing a number is to know all the divisors, is to represent the number using all its divisors. Okay? So for example, if I take a number, let's say 160, and I want to factorize this number, يعني factorize, I want to represent this number using all its divisors. Okay? So طبعا everything is divisible by 1. Okay? ماشي. So we know 1 is part of it, is always part of it. Okay? But is 2 part of it? Yes. So if I divide 160 by 2, the answer is 80. Divide by 2, the answer is 40. Divide by 2, the answer is 20. Divide by 2, the answer is 10. Divide by 2, the answer is 5. صح? And then 5. So these are the divisors of this number. This is the factorization of the number 160. ماشي؟ طبعا سؤال, why are you doing this? حتى يعني هنعرف. This is the introduction to understanding how RSA actually works. ماشي? So the operation that we have done now is to factorize a number. Factorizing a number is to find or to represent the number using all its divisors. ماشي كده؟ طيب, so this is easy. So this is 2 to the power 5 times 5. Okay? طيب, what is a prime number? A prime number is a number that has only itself as a divisor and the 1. صح? So in a way, you cannot factorize a prime number, okay, using anything but itself and the 1. Okay? So how can you represent 7 or 17? You cannot factorize 17 using any number other than itself and the 1. This means that this number is a prime number. طيب, so far so good. الدنيا بسيطة so far. طيب, factorizing any number can be done using the prime numbers. This is in fact what we have done here. If you look at any of these numbers, all prime numbers. Okay? All of these are prime numbers. So there is a simple theorem that says that any number, m, okay, in fact, can be factorized, okay, using prime numbers to power something. That's what we've done here. Okay, so this is a simple theorem that any number on Earth can be factorized using a set of prime numbers, okay, with certain exponents, arbitrary exponents. Okay, so that's a theorem, very simple theorem. تمام كده؟ طيب. Again, bear with me, and we're getting there. But if I talk about it without giving you these fundamentals, you will not be able to understand anything. طيب, what is the greatest common divisor? Okay, a greatest common divisor is to try to find two numbers, to try to find the divisors here and here, okay, such that these divisors are the greatest divisors that divides A and B. So, assuming, for example, that we have number 10 and 160. What is the greatest common divisor between 10 and 60? So it's 10. صح? It's because this can be factorized as 2 and 5, and this can be categorized as 2 to the power 5 and 5. Okay? So the common between them is 10, because actually 160 is divided, can be divided by 10. So this is 10. Okay? So that's the greatest common divisor, okay? Which is to find the divisor for this, to find the divisor for this, and then to find the overlap, okay? And then this will be the greatest common divisor. Very simple, okay? طيب very importantly بقى, if GCD of two numbers is 1, this means what? This means that لا, no. This means that these two numbers are mutually prime. But that doesn't mean that each one of them is prime. Okay? يعني مثلا for example, let's say مثلا the greatest common divisor between 21 and 160. Okay? 21 can be factorized as 3 times 7. And this can be factorized as 2 to the power 5 times 5. صح? Okay? Is there any commonality between the two? مفيش. يبقى the only one is 1. Okay? Does that mean that this one is prime? Or this one is prime? No. But we call them a co-prime. Co-prime or mutually prime. Okay? So far so good? تمام كده؟ طيب. This is the last one, but it's the most important one. Okay. طيب. What is بقى the totient of a number? The totient of a number. A totient of a number, we refer to it as phi of n. Okay? The totient of a number is the number of non-divisors. Okay? From 1 all the way to n. Non-divisors. Is the number of prime numbers that do not divide this number. Okay? طيب. What is this of 160? So we'll find all the numbers between 1 all the way to 160. Okay? Such that 160 is not divisible by this number. In fact, the only thing that divides this number is 2 and 5 and 1. The rest are non-divisors. Right? So this is in fact 157.
So not all the prime numbers.
لا, not all, لا. ماشي? This is the totient of n. طيب. What is the totient of a prime number? A totient of n is -1. خليكي accurate بقى. ما هو التوشنت البرايم نمبر is divisible by itself. صح؟ يبقى التوشنت of any prime number is n minus. ماشي كده؟ So we understand all these properties and concepts now. طبعا this is يعني very fast يعني introduction يعني. Okay? طيب. Given this بقى, what is the idea of RSA or public cryptography? Is built on one simple assumption بقى. It's built on one simple assumption. ماشي؟ if يعني طبعا احنا هنا we knew how to do the factorization of a number 160 very easily. Right? We start from the lowest prime number. We try 1, we try 2, we try 3, we try and so on. صح? But as you can see, we are always trying. صح؟ لا هو الفكرة بقى is there a systematic algorithm to do this other than exhaustive search?
Yes.
The answer is no. هو بقى this is the assumption of public cryptography. And then if I give you a very 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 large number ماشي 300 digit number, okay, and I tell you factorize this number, Okay? You will keep trying بقى. You will say, is it divisible by 2? If yes, that's good news because you have reduced the big number into half. Okay, and then you try to find another prime number that divides this. If you cannot find low prime numbers that divide this number, you will You will keep trying. ماشي? If I give you a 300-digit number that is not divisible by low prime numbers, then it will take you a very long time to come up with a prime number that divides this number. That's the simple assumption, but let's see how it's used. How it's used. طيب. The RSA is built, or it uses these 6 systematic steps. 1. Inside a source, the source will independently and secretly, locally will select 2 prime numbers such that each one of them is 300 digits. Very big number. Okay? Very big number. ماشي كده؟ These P and Q are not known by everyone locally. ماشي؟ ماشي كده؟ طيب. Number 2, calculate n. Multiply the 2 numbers. If you know the 2 numbers, each one of them is like 300 digits. You multiply the 2 numbers, you can get n easily. صح؟ if I give you n بقى.
Can't go back.
طبعا if I give you n, can you reach to P and Q? The answer theoretically is yes. طبعا الناس بتوع الكوانتم كومبيوتنج يقول لك لعبه piece of cake. طبعا بالنسبه لهم piece of cake طبعا. انما بالنسبه لنا احنا لا، يعني لا، it requires exhaustive search because you will try all the prime numbers that are less than this 300 digit number. You will have to try it exhaustively. ماشي؟ And that's the idea. There is no systematic algorithm that can guess P and Q from knowing n. This is the fundamental mathematical يعني basic rule that based on which the public cryptography is built. ماشي كده؟ طيب if I know this, طيب knowing يعني if I know P and Q I can get n. بس again يعني ماشي احنا we cannot guess P and Q, but how can we make it بقى reversible? How can we make the algorithm reversible? What do we do with P and Q with n? That's what we need to do in the remaining steps. طيب. Number 3, calculate the twoshent of n. We know that the twoshent of n, right? If a number is a prime number, the twoshent of a prime number is n minus 1. طيب. The twoshent of n is in fact, طبعا the twoshent, by the way, one thing I missed, the twoshent maintains the multiplicative property. Which means that the twoshent of n is actually the twoshent of P times the twoshent of Q. And we know that P and Q are prime numbers, so the twoshent of n is in fact the P minus 1 times Q minus 1. Very simple, صح? So far so good. تمام. طيب. Now بقى number 4, we will select E. E ده بقى هو البابليك key بقى. E بقى هو البابليك key. Such that E is co-prime with the twoshent of n. هتقول لي ده في tons of values هنا، صح؟ لأن التوشنت of n can be factorized as P minus 1 و Q minus 1. So in fact anything else cannot factorize the twoshent of n, which means that E has multiple values. Yes, you have degrees of freedom زي ما انت عايز for the public key. مفيش مشكلة. So we can select E such that E is co-prime with the twoshent of n. And this is very easy. ماشي؟ تمام؟ What's not easy بقى, and it requires a little bit of systematic calculation, but this can be done systematically, which is to calculate by the private key. So based on your selection of the public key, the private key is calculated such that D times E mod the totient of n is 1. Okay? We call D is multiplicative inverse of E, okay, mod totient of n. ماشي? And it turns out that this problem is very hard to do unless you know the totient of n, which requires the fact that you know P and Q. You don't know the totient of n. You know n طبعا, but you don't know the totient of n except if you know P and Q. Okay? So this way you can calculate the multiplicative inverse of E, okay, which is D. D بقى هو الايه؟ هو الايه؟ So this is number 6 بقى. D becomes the private key, okay, and E becomes the public key. That's it. تمام كده؟ So these are the steps. طيب. How do we do it بقى؟ خلاص احنا we calculated the public key and private key. How do we do the encryption and decryption? Okay, so the encryption and decryption are done simply by saying, okay, so the cipher is to calculate m to the power the public key, assuming that we're doing the confidentiality, يعني, we're using the public key for encryption. So m to the power e mod n. So we know n, of course, we know n. Everybody knows n, okay, and we know e. Everybody knows e, which is the public key. So we can encrypt the message easily. Okay, and then at the receiver side, we take the cipher and then we use the private key. So C to the power D mod n. Okay. By doing this, we calculate m. ماشي كده؟ طيب. How do we prove reversibility? How do we prove the reversibility? So this means that C. So we need to prove that C mod n will lead to m. What is C? C is m to the power e mod n all mod d mod n. Okay. So we need to prove that all of this is m, equal to m. Okay? So using the multiplicative property, we can in fact get the mod outside, صح? So we can say m to the power ed, okay, mod n. صح كده؟ Using the multiplicative property. تمام كده؟ طيب, what is بقى ED? Remember, ED is here. ED mod the totient of n equals to 1. What does that mean? This means that ED can be represented using some integer number times the totient of n plus 1. صح؟ مش ده اللي احنا قلناه؟ صح كده؟ Such that in 1 that this is the remainder. صح؟ So this means that this is in fact equivalent to the fact that this is I totient of n plus 1. Okay? Mod n. Yeah? So this can be by separated to m لوحدها multiplied by m to the power totient of n mod n. Okay? صح كده؟ So هو بقى جه بقى ليه لحد واحد اسمه بقى اويلر أما طبعا this is I هنا. I هنا ماشي. Any integer, any multiples of tangent of n. فجي بقى واحد اسمه اويلر طلع بقى theorem that this is in fact always one. Only if the greatest common divisor of m and n is 1. على condition هنا. يعني هو he proved that this is 1 okay if هو ما قالش if not مش هتبقى 1 يعني بس هو قال if this greatest common divisor between m and n is 1 then this will always be 1 which means that this will in fact be m. Okay?
So how to make sure that GCD
ايوه ده بقى السؤال. طيب practically can we ensure this؟ قال لك practically it's very easy. Why? Because n has 2 prime numbers only. So you just make sure that n as a message does not have p and q as divisors. Only p and q. Okay? So even if you want to guarantee this and force this, you can do some encoding to m such that in p and q are not divisors of m, which is it's easy and you have tons of degrees of freedom in that case. This condition, by the way, is missing in most of the books. They don't talk about this. But in fact, this is a condition by Euler. For Euler's theorem to be valid and it applies all the time, this is the condition. And you will see that you will use this in one of the assignments. You can use this to actually simplify your life. يعني I can give you I can give you مثلا an example. مثلا example على إن if you apply something like this in the problem, sometimes it makes it very easy. So if I tell you مثلا example, what is 2 mod 7? Simply 2. طيب what if I tell you 2 to the power مثلا let's say 90,000. 2 to the power 90,000, sorry. 90,000 mod 7. لا طبعا هتقول لي ادخل المود جوه وهي becomes 2 mod 7 اللي هي 2 to the power mod 7. طب ما عملتش حاجه.
We take the quotient of 7 which is 6. So
We can do it using this but there is a simpler way of doing this. يعني just which applies the same concept more or less. If you say that 2 to the power 90,000, it's in fact 2 to the power 3. Okay? And 3 times ايه بقى؟ 30,000 صح؟ Okay? Mod 7 صح؟ Now بقى enter the mod inside. Becomes 8 mod 7 صح؟ To the power something mod 7. What is this? It's 1. صح؟ Because 2 to the power 3 is 8. تمام؟ Mod 7 to the power 37, it's 1. So just by using يعني this the multiplication of this, I can make the problem much simpler. So this is one of the tricks that we use يعني. That's another way. You can actually calculate بقى the tangent of n اللي هو 7. You can do this as well. So these are يعني some tricks that you can use. In assignment 3 assignment 4, you will be able to do all these arithmetics. ماشي كده. So this is just to quickly do the the proof for reversibility of RSA. ماشي؟ طيب, last thing we talk about this example. So if I have the public key, the public key is 7. Public key is 7, and which is E, and D is 23. Okay, and N here is 187. طبعا 187. If I tell you what are the divisors of 187?
P and Q only.
what are P and Q? شوف, for a low number, for يعني let alone بقى يعني احنا we're talking about a 300 digit number. For a low number we cannot even يعني come up with it easily. Okay? For this it's actually I think 17 times 11, something like that. Okay, so if you try this on the calculator, you will get 187. But the main thing is that you cannot do it easily, okay? And there is no systematic algorithm that allows you to do this except brute force. ما فيش أي طريقة تانية. Okay, so that's the key. So if 7 is the public key and 23 is the private key, or the other way around, doesn't matter. Okay, so we can say 88 to the power 7 mod 187, so the answer will be 11. If I try this, so we can prove the reversibility very easily, assuming that this is the public key and the private key. We can reverse it if we want, there's no problem. Okay, so that's doable. طب دي طبعا عشان يعني ايه we can talk about this is bad how to compute the greatest common divisor for two numbers, okay, systematically using certain algorithm. So we can calculate the greatest common divisor for a number using a systematic algorithm. ماشي? But can we do the multiplicative inverse using a systematic algorithm? Yes, if we know the totient of n. We don't know the totient of n, we know n. ماشي? So to calculate the totient of n, then you need to P and Q. And P and Q is very, very hard to guess. Okay? So we'll stop here, and then we'll talk about this algorithm, because if I talk about it, I think you will...